Good. Welcome, everyone. It's a pleasure to have Leandros Perivolaropoulos here today. Thanks a lot for accepting our invitation. Leandros is a professor at the University of BAO and SnIa since 2010. He got his PhD at the Brown University in the US, followed by postdoctoral positions in Harvard at the Center for Astrophysics and MIT. He then became a visiting faculty at the University of Crete, a research fellow at the Demokritos Research Center in Athens, and finally associate professor at the University of BAO and SnIa. Leandros' research interests are theoretical and observational cosmology, modified gravity, and field theories, with a recent focus on the tensions of the standard lambda-quadrant-matter cosmological model. Today, he will present Hubble tension, a global perspective of measurements and models. Leandros, please, you can start when you're ready.
Okay, thank you, Leonora. It's a pleasure to be here. And, thank you for the invitation, which gives me the opportunity to present some recent work and some general perspectives on the field. I think these seminars are very important, and I really want to support them. And they have made a very good database also of videos, which is very nice for the community. So what I'll talk about today is I'm going to present a viewpoint, a global perspective of the current status of the Hubble tension, with emphasis on some new kind of grouping of the measurements and the models, and try to summarize the advantages and disadvantages of various approaches towards the Hubble tension. Now, the dream of every physicist is to live through a change of a standard model, to live through a situation where new fundamental physics are introduced, and especially if he or she are able to contribute in this fundamental physics change. Now, our generation has been fortunate to go through such a change with the introduction of the cosmological constant, which was a major change of the previous standard model, which was the well-known SCDM, which involved a flat universe containing only cold dark matter. Now, it may be possible that the new breakthroughs that we are going through, technological breakthroughs, and the new measurements we have may bring us close to live a second change of the standard model, since there are, as you all know, there have been lots of tensions being accommodated. But to understand what will be the probable new standard model, we have to look a bit back in history and get some lessons on how were the previous standard models introduced and how were they discovered, so they can follow similar kinds of approaches and see how we can come closer to this new standard model. So it's an interesting approach to look a little bit more carefully and see what are the characteristics of a new standard cosmological model where it appears, so that we can get some guidance for perhaps the next change of cosmological model. Now, the timing, it happens every few decades up to a few centuries, depending on how rapid technological breakthroughs appear. Now, the signals, they are usually, but not always, preceded by some technological breakthroughs that lead to new data, which produce tensions and challenges for the previous standard model. For example, for the previous standard models for the SCDM, it was indications from large-scale structural observations that the omega matter, the density parameter for matter, was less than 1. It was in fact 0.2 to 0.3. And there are other indications. For example, the age of the universe in that model was below what globular classes all the stars indicated, and only an age node of about 0.5 could accommodate these kinds of large age in this cosmological model. And finally, it was the discovery of Q node being smaller than 0 from supernova in 1998. Now, this new model, the lambda CDM, which emerged from these tensions, was predicted by various authors, but most importantly in this classic paper of 1990 by George Evstathiou, which actually pointed out much before it was clear that this was the real model, the cosmological model the cosmological constant as a new ingredient of cosmology. Now, when this happened, it was clear that there was some inertia. That is, there were lots of there was some data which were consistent with the omega zero matter equal to 1, supporting SCDM as a standard model. And there were some other more conservative models introduced, like mixed dark matter, to try to save the SCDM model. So it's natural to expect in every change of model some inertia in which people try to focus on data which support the previous model because it's usually more successful and it's more conservative to support it. Now, in order to make a transition to a new model, there should also be a simple and generic new standard model, which can actually, with very few new degrees of freedom, perhaps with 1 degree of freedom, which is new, can explain the new data and the new tensions. It turned out that in the previous transition, the corresponding model was the lambda CDM model, and this became the standard model for the last quarter of a century. But now, as I said before, there's probably a chance to make some, construct a new model, perhaps, if these tensions are really understood. Let me briefly remind you some history of other previous major shifts of standard cosmological models. We had, for example, the geocentric, which was one of the first cosmological models, perhaps the first cosmological model, to a heliocentric model proposed by Copernicus based on some data, the retrograde modes of planets, motion of planets, phases of Venus, etc. And this was followed by various other transitions, for example, for the heliocentric to infinite universe, from infinite to static universe. In fact, this was the only, perhaps, case where a change of standard model was introduced because of a theoretical advance, in which case you had general relativity. And this became, thus, the infinite universe became consistent with general relativity through the first model consistent with general relativity, which was a static universe, which was soon realized, in fact, that this was not the case, even though the cosmological constant was a very interesting introduction, new element, which turned out later to be the latest standard model that we have. Then we had from static to expanding universe with the new data from Hubble, the Hubble's law, and from Slipher, which discovered the redshifts, which showed that all redshifts seem to be existing. There's very few blue shifts, most of them are redshifts. Then we had from the expanding universe the introduction of inflationary Big Bang, using the CMB as data, as new data, the light element abundance, etc. Various other new data which forced us to abandon the previous model. Then there was the introduction of dark matter, a new degree of freedom based on galaxy rotation curves, gravitational lensing, and galaxy clusters. And latest, we have the lambda CDM model, which was introduced by various data. I just show here some of the latest confirmations of this model with the CMB, baryon acoustic oscillations, and supernova observations. And now we seem to be entering a new era where this lambda CDM model seems to also be facing a wide range of tensions, which may hint towards new degrees of freedom. And our role is to actually try to dig through this noise, I would say, because there are many tensions, noise of tensions, and identify those parts of these tensions which are coherent and may lead us to discover the proper new degrees of freedom which are needed to introduce lambda CDM towards the construction of a new standard model of cosmology. So this is not a simple task because of, mostly in this case, we have too many tensions which we have to somehow try to understand and focus on those which are relevant and try to ignore those which are not. And that's not a simple task. Now, these tensions are reviewed in this paper we have had recently with Fotinis Kara, where we review all these tensions, trying to make some coherent and picture of them, and perhaps this can be used to try to understand what are the new degrees of freedom that are needed for the identification of the new standard model. Now, the two most important and interesting tensions that exist at present are the Hubble and growth tension, which you see schematically here. For the growth tension, we have this so-called S8 parameter, which you see here, which indicates the strength of growth of perturbations. And you see that early universe estimates of SH8, based on basically on mostly on the CMB, provide an estimate of SH8, which is in this region here, and this is much, it's 2 to 3 sigma bigger than direct estimates from late universe measurements, basically weak lensing and other measurements. And the same situation happens also in the case of the Hubble tension, which is the most, perhaps the best known tension and perhaps the most strong discrepancy. It's at 5 sigma currently. And you see that there is a discrepancy between early time measurements based on the CMB and late time measurements based on more direct estimates, which are shown here. So the common perception is that because these late time measurements are direct, they are measured without perhaps assumptions, what one should do is one should shift the early time measurements and make them consistent with late time measurements. Now, this is a general approach which is happening, and I will argue in today's talk that perhaps this is not very much justified by the data. First of all, because the late time measurements are not all of them consistent with each other. There are some groups which are inconsistent from other groups. And second, that they also make some assumptions which are important and which are perhaps if they are broken, they can lead the late time measurements become consistent with the early time measurements. So the standard approach, which is change the assumptions of the early time measurements, make them consistent with the late time measurements, in this talk will be challenged, and I'll try to convince you that perhaps this may not be the best way to proceed. To understand now what is the proper way to proceed is to, let me see how this, is to, let me see, can you see the full, all of my screen, or is the upper part hiding? Do you see my screen?
Yep, we can see your screen.
The full screen, okay. Anyway, so let me review now briefly the methods for measuring H0, and based on that, we can try to see the assumptions that are involved. Now, the most precise but not necessarily accurate method for measuring directly and locally H0 is the distance ladder approach, in which you measure this apparent luminosity of standard candles, this this apparent magnitude, and you also then compare this with the luminosity distance, the absolute magnitude, which can then be used to find this relation, because this is the Hubble free luminosity distance. So we have the absolute magnitude supernova or standard candles, and here is the Hubble parameter. So measuring this apparent magnitude, we can have information about the combination, this combination of calligraphic M that you see here, which is the sum of the absolute magnitude plus the Hubble parameter. So what is usually being done, one measures the apparent magnitude, then measures locally using astrophysical systems below the Hubble flow at smaller redshifts, the absolute magnitude, breaks this degeneracy between M and H0, and then uses this parameterization of these cosmographic expansions to measure these parameters Q node, H node. So this is measured, and the basic assumption hidden here is that in fact this this absolute magnitude you measure in astrophysical scales is the same as in Hubble flow, at larger redshifts, where this relation is valid and where H node can be measured. Now this assumption is usually not always justified, actually, and so it is something that one has to take into account when evaluating these models. Now this leads to this well-known measurement of H0 73.04 plus or minus 1.04, which is the most precise measurement of H0 using local measurements. Now, the second approach is to use the standard ruler, sound horizon standard ruler, which leads to this relation between the sound horizon and the angular diameter distance. And here you measure RS by assuming two things. The first thing you assume is that RS is properly calculated, the sound horizon is calculated properly using the standard early times standard model assumptions for baryon photons and cold dark matter, and also that the evolution, the angular diameter distance, is consistent with lambda CDM. So you make two assumptions, one about the sound horizon, and the second about the evolution of the expansion rate of the universe in accordance to lambda CDM, in accordance to this to the CMB best fit parameters. As you see here, there are two assumptions which people prefer to play with when they try to address the Hubble tension. Most of the approaches is to either change the sound horizon or change the Hubble expansion rate from recombination to the present time. So that as changing this assumption, you also can actually change H0 according to this relation in which theta s, the sound horizon angular scale, is measured and fixed. Now, based on that, this leads to the well-known result of H0 according to Planck 67.36. So we have three different assumptions involved in these measurements. One is the absolute magnitude of supernova, is the same before and after the Hubble law, and the other is sound horizon and the expansion rate. So there's clearly a degeneracy here between RS and H0 and also an A or Z, and this is how people usually play. Now, in addition to these classes of measurements, there are one-step methods which do not require the presence of sound horizon. And so these methods are based on, for example, various more direct measurements based on time delay gravitational lensing, mega masers, gravity waves, cosmic chronometers, other standard rulers like the sound horizon of the time of fecal matter radiation, and various other methods which are of interest. Now, these methods so far have not attracted very much attention. It usually assumed that they are consistent with distance ladder measurement. Now, I tried to challenge this assumption recently by collecting all these measurements and trying to see what kind of value of H0 they favor. Do they favor the distance ladder method, or do they favor the early time measurements of the sound horizon? And these, so the questions that I wanted to address are the following. What are the current distance ladder measurements of H0? If we group them together, are they consistent with each other and with the SnIa measurement, which is the most precise measurement? And the second question was, what are the currently available one-step measurements of H0, which are independent of sound horizon and distance ladder? Are they consistent with each other, first of all? And also, are they consistent with the SnIa measurement or with the sound horizon based on measurements? So the question is, this is a part of measurement which has not been individually discussed so far. So I try to discuss this class of measurements separately and see what do they say, what do they tell us. So I collected a compilation of all the measurements of this type I could find during the mostly during the last 5 years, but there were a couple also previous measurements which are very big intervals, but I focused on the last 5 years, and these are 33 measurements which try to measure H0 using a very wide range of methods, including lensing, gravitational waves, dark sirens, kilonova, H2 various other methods. So this is 33 measurements, and you can see them here for H0. By just a quick look, you can immediately see that many of them, in fact, most of them have a 6 in front, which indicates that they tend to favor the measurements coming from the CMB, from the early time measurements. So this is a surprising result for me, at least it was, because the common perception is that all local measurements or other measurements compared to distance ladder would favor, would are independent of the sound horizon favor the distance ladder measurement. But it turns out that this is not the case. So this is the compilations of 33 measurements. You can look at subsets of those, but they actually do not change the conclusion, which is, as I will say, a favor of the consistency with the early time measurements, CMB. And with the exception of these two outliers, which seem to be, according to a chi-square analysis, somewhat less consistent with the others. And the one of them is the TDCOSMO I measurement, which gives a very precise, actually, measurements of H0 74.2 plus or minus 1.6. It turns out by later papers of the same collaboration that this indeed makes some assumptions which can be viewed as systematics. So at least the uncertainty of this measurement should be much bigger than 1.6. And also the central value has also been challenged by recent other measurements like this latest lensing with slugs, trying to model the mass profile of the lens. And also the second is this measurement here for mega majors, which is also quite precise and has been produced by the Mega Major Cosmology Project plus some SUS contribution, Dan Skolnick and Adam Rees, which give a highly precise measurement, which is not so much consistent with the other two mega majors measurement. So this is another point which indeed turns out that if it's subtracted, the rest of the measurements here are becoming much more consistent with each other. So these are two, which I call outliers, and we will discuss later on. Now, the distance ladder measurements, on the other hand, are grouped together, you see, with various calibrators and various distance indicators shown here. And you see that essentially most of them, if not all, have a 7 in front. In fact, 73 and bigger, most of them. And then you see a clear distinction in the values of H0 that are favored, with the exception perhaps of the recent measurement by Friedman et al. And their group, which is shown here as separate papers, which indicate that most of them, the vast majority of them, favor a different best fit value of H0 than these one-step measurements. So in fact, if one makes a distance ladder weighted mean, this is 72.8 plus or minus 0.5. And the one-step measurements provide a 69.0 plus or minus 0.5 kilometers per second per megaparsec. And if the two outliers are removed, this drops down to 68.3 plus or minus 0.5 kilometers per second per megaparsec. So you see that something is happening here. You can group the measurements here and find that, in fact, there is perhaps the tension is perhaps between distance ladder measurements and everything else, which everything else includes sound horizon measurements and all other one-step measurements, which one can look in the literature. Here you see a plot per year of the distance ladder measurements with red compared to the one-step measurements in blue. And these are binned per year here. And you see that with the exception of TDCOSMO I, which is above the distance ladder measurements of that year, the rest of them are consistently below the distance ladder measurement each year, and they are more consistent with the Planck measurement rather than the distance ladder SUS measurement, which is this green point up here. Now, the bands here correspond to the best fit of all the measurements of one step for the blue band and the one step and the distance ladder measurements for the band which is red somehow. So we see that one step measurements are surprisingly consistently lower than distance ladder measurements. Then here you see the probability distribution of these measurements. These are for the one step measurements here. You see the median is close to 67 here. And while for distance ladder measurements, they are much more consistent with each other. And they favor this value of the median of about 73 kilometers per second per megaparsec. These distributions are quite distinct from each other. You see there's a clear peak here and the others are broader, but has a clear peak at the CMB Planck 18 measurement. So one can actually also do a KS test and so find the p-value 0.001, which indicates that it's a very low probability that these two samples are drawn from the same probability distribution. It is less than 0.01%. Of course, this by itself doesn't necessarily say that there's a problem because the one-step measurements are very diverse. But in any case, we did this testing just to indicate one more point, which could also be taken into account, or other people may choose not to take it into account because it was more or less expected that there would be some difference in the probability distributions. So this is from this paper that I mentioned before, which has appeared recently on the archive. Now, one can actually also look at the robustness of these results and look at perhaps some outliers. So one can look at the full sample. You see it has a chi-square per degree of freedom of 1.37, which is shown here. You see 1.37 here, sorry. Here. And if you remove the two outliers, then the chi-square per degree of freedom drops to 0.95. That's why I call these two outliers, because if they are removed, then the rest seem to be much more consistent with each other. And also H0 becomes 68.3. And there are various subsamples. For example, we can look at the gravitational wave subsample and the full sample excluding gravitational waves. We see that they are relatively also, in most cases, they are somewhat low, depending on various subsamples. So you can get an idea of what favors what. You see, for example, that there are various groups which have different degrees of favoring the CMB value of H0. Now, so these are the outliers again, as I showed before. So one-step measurements become self-consistent and are fully consistent with the sound horizon scale if two outliers are removed. But even before that, they're again quite indicating a lower value of H0. So now we can go to so it looks like the distance ladder method may be a method which seems to be distinct from all other methods in terms of results. So it's interesting now to see what are the possible Hubble crisis approaches which are currently being used. So we see that we have this usual plot from Planck 18 results. We have here the distance ladder measurements, which is typical with all other measurements. You see this data point here. This is actually a bit older. It's slightly lower, as you know. And now this is the inverse distance ladder plot for h of z over 1 plus z. And you see this is calibrated from the sound horizon. And you see it's consistent with the BAO data because they use essentially the same standard ruler. But they miss, of course, this point of distance ladder by the SnIa team. So the question is, how do we make these two measurements consistent? That is, this curve here calibrated the sound horizon with the SnIa data point. One approach is directly to just shift the SnIa measurement down and towards the lower values of H0 by assuming, for example, that there are some systematic or that the absolute magnitude supernova is not the one that is being assumed, but something else, either because of some physics change or because of some systematic. Now, if we shift this point down, we have the additional bonus of making it consistent with one-step measurements, which involve non-sound horizon. So in fact, the rest of the distance ladder methods actually will be consistent with this new, this shift of these measurements down. Alternatively, we can change the sound horizon scale, the calibrator, and in that case, the whole curve will shift upwards. But in that case, we have to think how to make this new measurement of H0 based on this approach consistent, first of all, with early time calibrators, the time of equal matter radiation horizon scale, and also all the other one-step measurements which seem to favor lower values of H0. So this approach has to face this challenge also, how to make it consistent with these other one-step measurements. And the third approach is to actually deform. As you know, this has been very much used because it's the most obvious approach. Deform H of Z and make it consistent with the Sh0ES measurement. This has, however, as most of you know, is faced with serious challenges. For example, it has problems with BAO data, Barnett oscillation data, has problems with growth data, as we see in these two papers. But most importantly, it misses these one-step measurements, which show a lower value of H0. And in addition, it has to also match the rest of the supernova measurements, which, as you see here, this is an artist's view, it's not real data, which based on the calibration of distance ladder calibrators like Cepheids, it's not only this point which should be here, in fact, there are also all the supernova measurements of H of Z, essentially, which should also are also there, because the calibrator calibrates not only at Z equal to 0, they calibrate all the redshifts of the supernova. So this deformation has to also fit all these other data points. And it's obviously not possible to do that, because here you have the BAO data and all the other similar, there are many more points here, of course, and here you have the supernova data. These are inconsistent with each other, so you cannot fit them simultaneously by deforming H of Z. You will either fit one or the other. So this is another paper we had recently, which we tried to highlight and explain this point in more detail with data points. These are the residual distance moduli, luminosity distance moduli, which can be obtained from both baryon acoustic oscillations data and from supernova data, because we can convert the angular diameter distance to luminosity distance using this usual relation. And here you see that this is this band here on top is the band coming from the Planck measurement of based on the Planck lambda CDM model. This is the Sh0ES lambda CDM model based on the best fit distance moduli coming from the Sh0ES measurement, which involves also the calibration of the supernova. And here you see the data of the residual distance moduli coming from the baryon acoustic oscillation data, these blue points here, compared to the supernova bins in similar bins. And you see there's inconsistency, and this is a model which tries to interpolate between the early time measurement of distance modulus at the time of recombination and the late time measurements coming from supernova and baryon acoustic oscillations. And of course, you see that it's doing well at early times at high redshifts, but at low redshifts, it has to decide, will it favor the baryon acoustic oscillations or the supernova data? And there's a deformation, usually there's a compromise, but the end result is that this class of models do not provide a resolution of the Hubble tension, because they have to fit simultaneously data which are inconsistent with each other. There are other models which interpolate, which do a little bit better, like the lambda SCDM model. You see, it does a more abrupt change and tries to be consistent with the supernova data, which have smaller error bars. But even this class of models, like lambda SCDM, still have this problem of poor quality of data. So it looks like of data fitting. So it looks like the solution of the Hubble tension will involve either shifting one calibrator or the other set of calibrators towards either moving the supernova Cepheid calibration upwards here. So either move this line up or move this other line down for consistency. Otherwise, you cannot have at the same time both features happen. And here you see that some comparison of consistency between at various distance redshift bins. You see that the BAO data and the Pantheon data are inconsistent with each other at here at low redshifts between 0.1 and 0.8. At high redshifts, they become a bit more consistent. That's because they have bigger error bars, so there is some consistency for H and omega matter. And you see that for BAO data, there's no internal tension essentially, and neither for the For the Python data, there is some internal tension, but it's much smaller than the tension between BAO and supernova data. So let me remind you a little bit of the problems that are faced that the sound horizon data. So one approach here would be to just change the sound horizon and shift it in such a way that it becomes consistent with the, so the BAO data becomes consistent with the supernova data. Now, the problem with this approach, as I said, is first of all, it doesn't fit the one-step measurements, but also there are many other problems which are summarized in this paper by Sunny Vanosi, which 7 hints that early time new physics alone is not sufficient to solve the Hubble tension. This is published in Universe in a volume that we edited with Jackson and Leonora, and has attracted significant attention from the community based on the citations it has received. And here you see the problems. I'm not going to go through them in detail. What I'm going to say, what I want to focus on, is the fact that according to this recent paper by Vivian Pullen and et al., these are who made a review of late time models. We see here the best fit values of H naught according to this new degree of freedom for the sound horizon, and you see that all of them, even though they try to approach the SH0ES measurement, they still are struggling to reach that. And the most important point is that these measurements are in fact post-dictions, in the sense that these measurements take into account the measurement of H naught by the SH0ES team, and using this measurement, they try to shift towards the measurement there. So in a sense, since they take into account this point, they are effectively post-dictions, not so much predictions. And also this point here for the lambda CDM is written here as if without taking into account the SH0ES measurement. So it's not very fair to compare this point here with these points, which use the SH0ES data point as a data, in which case they are shifted towards that. So this class of model has this problem, even though it's a very nice, it's apart from that, it's an interesting approach to change the calibrators rather than changing the deforming H of Z. So it has in principle a good type of approach. So the other approach is to shift the, as I said, to shift the absolute magnitude of supernovae towards lower values. So there are two ways in this case. One, this part here, this is the distance ladder measurement of the absolute magnitude of supernova, which is here, and this is the inverse distance ladder value of the absolute magnitude of supernovae using the H node from the CMB, this H node here. So if you use this H node and find this, find the absolute magnitude of supernova, you find these data points. These are bint, of course, and you see that they are lower compared to the one measured by Cephites, which is up here. So there are two approaches here. One is to say that this is in the context of shifting the late time models, this another process, to a higher value, to a lower value. You can either say that all these are wrong, all the distance ladder measurements are wrong, and this should go down because of a systematic, or you can say that in fact both of them are correct. Both the Cephite measurement here is correct, and the inverse distance ladder measurement in the Hubble flow is correct. And what really happens is just a transition of M due to some physical effect, and this is what is this is the origin of the Hubble tension, which we assume that the supernova absolute magnitude is in this region, but in fact, because of this transition, the true MB is in this region. So this is so-called the local physics transition hypothesis, which, if implemented, would just change the H node measured by distance ladder measurements to simply one consistent with the CMB due exactly to this physics transition. Now, what could be the origin of this transition? The simplest approach would be that it could be some fundamental physics change, perhaps a gravitational transition due to some, let's say, vacuum decay, or due to some discontinuity in the non-minimal coupling in a scalar tensor theory. Now, if we accept this is a gravitational transition, then we can actually also solve the growth tension, because a weaker gravity emerging in this approach would also resolve the growth tension. So how do we proceed? How do we test this hypothesis? The only way to test this hypothesis is to reanalyze the source data with new degrees of freedom. That is, to allow in the analysis for a possible change of the absolute magnitude of supernova, and hope that this will happen also not exactly at 0.01, it may happen at some redshift a little bit before this exact transition. And if we allow the data, they may show us perhaps a transition a little bit earlier before 0.01. And maybe if we are lucky, we can see this transition inside the source data. Now, this I think is a very important thing to do, because this would test this whole class of models. Unfortunately, very few studies have been done to reanalyze the source data with new degrees of freedom. Now, we have actually initiated this in some papers, including this paper, which is called a reanalysis of the latest source data. And we actually try to evaluate this absolute magnitude of supernova, this MB, using the measured apparent magnitude minus the measured distance modulus of Cepheids in these co-host galaxies, which are evaluated in two ways. One way is to derive mu I as a parameter in the source analysis without assuming that MB is constant, is fixed, like the source did. They fixed a bit. They said this is the same for all galaxies, either before or after the Hubble law. And you do this analysis, and then you see what they actually measured for the MBI, for the MB of the supernova. Alternatively, we can allow a transition, not enforce it, but allow it and reanalyze the data to see if the data would favor this kind of transition. Now, if you don't allow this transition, you get this distance, this absolute magnitude of the supernovae using the source analysis, and you see they are more or less all consistent with this band, as we said before. And of course, there are some points which are not exactly in, but most of them are consistent. Now, if you do the analysis by allowing a transition at some distance, you vary the distance, you see that if you allow it at some distance close to 45, 40, 48 megaparsecs, then these two last hosts spontaneously drop down and become, with big error bars, drop down and become consistent with the inverse distance ladder approach. I'm not going to say that this is the way to proceed necessarily, but I'm saying that you see interesting results appear if you put new degrees of freedom. Now, what degrees of freedom would be those? It's a different story. We tried a single degree of freedom, which would be just change the supernova absolute magnitude, allow it to change. But we could also allow to change the Cepheid magnitude, or whatever, simultaneously with supernova. We haven't explored this very big area of new models for fitting Cepheids. But we argue that even if we do the simplest possible thing, show something. Shouldn't we look at different models, different new degrees of freedom in the analysis of the Cepheid data? We argue yes. Now, what this would be, this is an open issue. This is the simplest example. We already see something here. This is not the final answer. There are many other approaches to do here, which would introduce new degrees of freedom. But this is a virgin area. Unfortunately, this is almost virgin. Very few people have worked in this direction, in contrast to the other models, the other classes, which a huge amount of studies are present, especially for the deformation class. And I would say that one should pay a little bit more attention in this kinds of approach. Now, this is very straightforward to do that, and which would involve, for example, how do we analyze the source data? We have one equation for the Cepheids, which is the apparent magnitude of Cepheids of the ith Cepheid of the jth galaxy, which is this equation involves metallicity. This is the parameter for the metallicity, the period luminosity. This is the period of the Cepheids. This is a parameter which connects the period with the luminosity. This is the essentially the absolute magnitude of this Cepheid, the 0 point here. And these are the distance moduli which are to be fit. And the same distance moduli are fit for the supernova because they are co-hosted with the with the Cepheid here in this relation, and then we go out to this below the Hubble flow, this relation. And if you go out to the Hubble flow, you have this equation which connects this apparent magnitude of supernovae with the distance, luminosity distance, and with the H0. So we have here several data. We have 3,492 equations for this today, and there are 47 unknown parameters which are shown here. They include the distance modulate to the galaxies which host both supernova and Cepheids. And so, of course, you will say it's a huge amount of parameters, but fortunately, this is not a problem because you have a system to fit. You have a chi-square which is linear to the parameters, and this can be done analytically. If you want to minimize chi-square which is linear to the unknown parameters, you don't need to do anything, but there are just simple formulas which give you directly the best fit values of this parameter analytically. It's in a laptop. You just apply some matrix multiplications, which give you directly the best fit parameters and their uncertainty. So it's a matter of seconds to obtain all these best fit parameters and get the value of H0 73.04 plus or minus 1.404, which is the well-known SUS result. We reproduced it very nicely. It's very simple to do that. Just we have it publicly available. Our code in Mathematica is publicly available. It takes a few seconds. Everybody can download using from our paper. Now how do you put in the new degrees of freedom? You allow, for example, one or many of these parameters to change at a given distance or a redshift. That's one way. Of course, there are many other ways, but I'm just saying one way. You allow them to change at a given redshift from one value to the next. For example, if you want to allow MB, the supernova absolute magnitude, to change, then you change these equations to these two equations, where you have MB bigger and MB smaller at a bigger distance or a smaller compared to the critical distance, which you vary as a parameter also if you want. And then you find what are these values, MB larger and MB smaller. And you have a new vector of Q of parameters, and you find the new best fit parameters. What you find now here in the case of, as I said before, in the case of, if you allow, for example, a change at MB about D-critical, about 48 megaparsecs or bigger, you find this at H0 spontaneously drops down to the value consistent with the CMB, with much bigger error bars, of course, because there are only two hosts which are there. And so you have a prediction here for H0 in the context of this model. This is a prediction. There is no input about the SUS point here. Just drops spontaneously to the value supported by SUS. And you get this best fit value of H0 by just introducing a new degree of freedom, allowing MB to change, just allowing. Now we also have another recent paper which highlights it a bit in some more detail using, instead of putting arbitrary value of MB change, you put a change of G, the gravitational constant, and you see how it affects both the period luminosity relation and the absolute magnitude of supernova using some theoretical models. In that case, you also find that if you allow this G to change, now you allow G to change, not just MB, the absolute magnitude of supernova, then you find in that case again that you have a change, a drop of the predicted H0, which is consistent with H0, and this again is a spontaneous effect, not an enforced effect. Now, if you also want to enforce the effect, make a post-prediction, you can do that also. In that case, you get a several sigma preference for this model compared to the vanilla baseline model SUS has used, and you get a prediction, a post-prediction, I should say, for H0 68.2 plus or minus 0.8, which really is in very big tension, almost 5 sigma tension with the SUS data without the, and it has a better chi-square, of course, because it also is favored by the SUS data point. Now there are other approaches like this one by Radoslav Wojtak, who has also tried to analyze the SUS data by now allowing the color parameters and the color parameter and the stress parameters to change between the subset which is in the Hubble flow and the subset of supernova which is not in the Hubble flow, which is roughly at redshift 0.01, about 40 to 50 megaparsecs, the same as we actually do, but he just wants to split this in this way, which is almost equivalent. And there he also finds that there is a difference in the color parameter, which is in the calibrator sample compared to the color parameter in the Hubble flow sample, and they find a statistically significant difference, depending on the model that they use, between the two samples. So this is an independent demonstration that perhaps something different is happening in the Hubble flow compared to the things that are happening at astrophysical scales. And also they tried then to also change this CRF parameter, which is some reference parameter, color parameter, and they also find in that case that the Hubble parameter can also be affected significantly by being lower if this parameter is changed. And there's a discrepancy between the two values of the color parameter. Now, the future, so this situation will hopefully be be clarified in the future with the new measurements which everybody is expecting. And the most interesting experiment, in my opinion, observational probe, is the JST probe, which is expected to refine distance ladder using higher Z Cepheids and supernovae, and hopefully try to pin down this probability, clarify this probability, because you see, for example, when only two hosts there at very high Z, it is hoped that perhaps using more Cepheids at higher redshifts, it may be possible to identify and look for this transition if it's really there, because we find some hints, but of course, statistically, it's a very low probability so far, so we cannot say anything. But with the advent of JWST, it will be possible to say something more precise about whether in fact there is such a transition there or not. Euclid, of course, is a well-known also alternative probe, which mostly, however, will constrain H0 through bioacoustic oscillations and weak lensing. Also, ground-based surveys, LSST and DESI, are also going to provide some hints, mostly about the lambda CDM model itself of higher redshifts, but also at lower redshifts will be an interesting thing. We have the next generation of CMB experiments. This will test mostly the early dark energy models and see if the predictions they make about the spectrum of the CMB at high L will be verified. Also, gravitational waves are also another one-step road which will be refined soon, and we'll see if it confirms what we find so far, that one-step measurements favor a low H0 or not. And so this will bring me to the end of my talk with the conclusions, which are the following. First of all, I argue that the Hubble tension is a tension between distance ladder measurements and all other measurements of H0. The resolution of the Hubble tension most probably requires a reanalysis of also the distance ladder measurements, introducing new degrees of freedom for the identification of new physics or systematics. A late transition event involving sudden change of supernova luminosity and or the gravitational constant parameter at Z less than 0.01 is a hypothesis that deserves further investigation by reanalyzing the SUS data and the new data that will appear from JWST with new degrees of freedom and see if they tend to favor any interesting effects or not. And some preliminary studies indicate that there are hints in the SUS data for such an ultra-late physics transition. Thank you for your attention, and I'm ready to answer possible questions or discussion.
Thank you so much. Thank you for the very nice talk. So I would like to start because I think I disagree with your interpretation of the one-step H0 measurements. If you can go back to the list.
Here it is, yes.
Yeah, okay, so it's true that the fourth digit is always around 6, but the error bars are like gigantic, and I think this is why they don't get much attention. And there are a few cases where the error bars go below 3 kilometers per second per megaparsec, but I think these are combination of datasets, like Philcox for sure is a combination with CMB lensing supernovae in BAO. Pogosian is using the value of the omega matter h squared measured by Planck. All the other measurements are error bars that are much more larger than 3, so they are in agreement with everything. So that's my first comment.
Okay, let me answer that.
Yeah.
I agree that in fact that the error bars are, if you look at each individual measurement, they're quite large, and that's why they didn't attract any attention so far. Now the thing changes if you combine them. What I did is to combine all these measurements, which most of them are diverse and independent, to combine them and then see what is the combined weighted mean of those and the corresponding error bar. And the surprising thing that in that case, you do find something which is interesting.
Sure, but
Now,
I mean,
regarding the other point you mentioned about the Pogosian et al., I agree that this is indeed based on the time of equal matter radiation horizon. Perhaps it's not clear if you can classify this as completely independent from the sun horizon. But I want to point out that even if you remove these points, which I did, because you see one of them favors a high values of, actually both of them favor relatively high values compared to the CFD. Even if you remove them, the conclusions do not change. And the nice feature about this analysis is that because there are lots of points, 33 measurements, even if you remove selectively some of them, the conclusion doesn't change. It's very robust. As you see in this table that I showed afterwards,
sure,
which I
but
used various subsamples, the things do not change very much.
okay,
Subtract some things and they say you get the same conclusion.
okay, my problem is that you can't really combine them because it's not true that they are not independent. So most of them are using the same things. Like here you have all the strong lensing measurements and they are completely overlapping. Okay, when you do the mega masers, they are measuring the same things, so you can't combine them as they are. So here what you should do, okay, some of the measurements are like updated measurements, oldest one. So I think what you should do is look at every measurement independently and then average them or choose, okay, among the same group and then average them all together. So I
You
don't.
can do that. I've done this already here. You can see in this table here. You can see I put gravitational waves in one group. For example, TD lensing all here. Cosmic chronometers one group. So I've done this. It's very simple to merge them in different ways. But whatever you do, you always end up with something which is below 70, clearly below 70 with smaller error bars. So it's a good thing to do, I agree, but they seem to be more or less robust, in my opinion, at least. But of course, it can be other analysis by other people of the same data set, or of even better, and perhaps doing a quantitative analysis disprove my conclusion. The field is open to what I could do is this. But of course, if one wants to disprove this, one should do another analysis which will show that this is not correct. But I tried to do various versions of that. So far, I wasn't able to really conclude that there is consistency with this analysis. This analysis is a very different, clear sample. You can see it here. Whatever dependence you choose to do here in this plot, you are stuck that the blue points will be below the red points. What
Sure,
can you
but
do?
look at the
Can
error
you make
bars.
the blue points above the red points?
But my point is that if you look at the error bars, they are in agreement absolutely within 2 sigma with the measurements of 74. So I don't see this disagreement.
Well, okay, that's true. That's
This.
true for each year. If you look each year separately, you see that if you combine the years, then things change.
That's my
Each
point.
year, every year will be below. It's very strange.
I agree. I think we agree to disagree. My point is that,
Okay.
in my point of view, you can't combine the things that you are doing, but we will see this separately offline. Okay, Indranil.
Hello. So I had a question regarding the proposed physics transition at 150 million years ago, if I understand correctly. I was just wondering what impacts that might have, if you had, I don't know, a 5% change in the capital G, within the solar system or on the Earth. And if you thought about this at all.
Well, yes, in fact, first of all, this change can happen with very relatively low value of delta G. What the data indicate as a allowed change of delta G over G is about 5 to 10% depending on the measurements from nucleosynthesis. So it's not very much constrained. If you have a 5% measurement, it's within allowed limits, because you notice here.
No, from nucleosynthesis, I agree. That's why I was asking if you thought about like what impacts it might have like terrestrially or in the solar system.
Terrestrially, what you can constrain is only the time derivative of G, and that is very much constrained, of course. The time derivative of G is extremely constrained to several, but I'm not talking about time derivative. What is needed, if there is a transition here, the time derivative of G at the solar system is exactly 0, so you have exactly general relativity. If you imagine, for example, a vacuum decay, which goes to a new vacuum, in the new vacuum you again have general relativity happening because G is constant.
Yeah, but what would happen to the Earth in the meantime while G dropped by 5%?
Well, there are various models which can achieve that. One possibility would be a late phase transition, or you can have. Let me see if I can provide.
No, but I understand theoretically can be done. I was just wondering, like, what impact it would have, or I mean.
Well, what impact it would have, it would, of course, obviously disturb the solar system. It would be a disturbance of the solar system, which would cause some cataclysmic events of meteorites. And in fact, I have a paper which I try to predict using this transition what kind of effects it would have in the solar system. I tried to simulate some events, and okay, this was an attempt to do that. You wouldn't expect. Some observers at the time would see that, and one claim would be that these meteorites which had to appear due to this disturbance could be the origin of having events on the Earth which are known to exist by geological. There are some epochs in the epochs of the solar system because they have increased number of meteorites, and one of them is supposed to perhaps be the origin of the disappearance of the dinosaurs.
Yeah, but this is too recent, right? Because that's only 65 million years ago, which corresponds to 20 megapascals.
I agree. It's too recent, but I'm just saying that it's possible in principle to have these kinds of events. It's not something that I'm not saying that. Okay, the analysis I said 150 million years ago, it was just one model. If you do different kinds of models, in the future you can find different. So it's the simplest model, which gave these kinds of hints. If you do a more detailed modeling then you can find, of course, different kinds of signals. But the simplest provides about 50 megapascals. That's just the simplest approach.
Okay, thanks.
Thank you. Marie-Noël?
Yes. Hello.
No?
Well, hello, Andrews. I would like to speak about a small problem. You cited the lithium problem as a cosmological tension in your first slide. And I thought this had been solved by astrophysical considerations. Is that correct, or where I'm not an expert in lithium. What is your point about that?
Okay, I'm not an expert either on this particular point, but my understanding is that this issue persists. I don't have to offer any more details than you would probably have. My understanding is until a couple of years ago that this problem was still existing. But again, I cannot really say much about this particular point. I'm not sure it is related with the rest of the issues that I was talking about. Perhaps it may be related in changing the bounds of the gravitational constant from delta G over G from nucleosynthesis. May be a little bit bigger or a bit smaller. But apart from that, I'm not sure it's related to the approach that I did today.
Yes, you just showed a link to this problem. Thank you.
Yeah, that's an interesting point. Yeah. Okay.
Goodbye.
Thank you. Vivian?
Hey, thank you for the talk. I just wanted to comment about your what you said about the figure that we put in the review, where you have the list of H0 measurement. I agree that it's not, the statement is not, you should not compare the value of H0 reported here with the blue band, and in order to estimate the tension. I mean, this is explicitly stated in the paper. Of course, the points here include the values of H0. And so if you want to estimate the tension, then what you have to do is use different metrics, and that's why on the same figure, in fact, we show frequentist-based metrics, or you have to use another metric. The lambda CDM point, by the way, does include the H0 as well, but this is more for representative, just for an illustrative purpose of the values of H0 that you can reach if you include the value of H0, but if you include the value of the supernovae magnitude in the calibration. But I absolutely agree that then, once you've done that, you should not compare the red points and the blue band. You have to use a different way to quantify the tension. So I think this is clearly stated in the paper. But then I had a question about the. And by the way, just to say, the reason we claim that early dark energy may or may not resolve the tension is based on the fact that it is able to leave the CMB data unaffected while reaching high values of H0. The fact that that's really the key. It's in the chi-square that you see that, not in the value of H0, really.
Exactly, I understand. This is the goal. But can you mention exactly what metrics you mean here in this? What would be the metrics that you implied? I forget exactly what you mentioned in the paper, because a naive approach is just to compare these data points with the range of shoes. That's what we.
No, but yeah. So if the most naive thing you can, so if you want, it depends. If you want to be Bayesian, what you would do is you don't include the value of H0. You do an analysis of Planck's, BAO, and whatever, and then you can use, I would not use something that is Gaussian, but I would use a non-Gaussian because the posteriors are non-Gaussian, but you can do that. And the Bayesian is going to tell you some level of tension. And then you can do the frequentist approach is based basically on estimating the impact of adding the shoes data on the chi-square. The rule of thumb, if you add a data point, is that including your shoes data modeled as a prior on MB or H0, for instance, for simplicity, should change the chi-square by 1, the rule of thumb, basically. You can do that in a way that is better, that is exact. And so you just compare the chi-square with and without the shoes measurement, basically. That's the basic idea. And the inclusion of additional data points should not affect strongly the chi-square of your data. That's the idea.
Okay.
And it's the frequentist version of a model comparison, basically, of a tension estimate. And then the other thing I wanted to know is in your model that has a transition, what is the value of H0 that you would reach in the end? Is it 67 or is it 73?
Well, as I said here at the end, in this particular simple model that I showed, it would be 67. I mean, that's you see here, if you have here in this plot here that I showed, you see here this, if you have a transition at the critical point of DC, let's say around 48 to 50 megaparsecs, then the predicted value of H0 would be 67.
Okay.
So in this approach, what we change is the distance ladder prediction from 73 is changed to 67 spontaneously without using any information of H0. The data just drop by themselves to the value which practically almost exactly the same as the CMB. Now the question is that to see this number, you have to take into account to put in these new degrees of freedom in analyzing the SUS data. And that's a crucial thing. I mean, this whole message I'm sending is basically reanalyze the SUS data with new degrees of freedom and they will speak to you. If you don't allow these degrees of freedom, the data will never speak to you.
Okay, no, I was curious. Good. Thank you.
Let's thank Leandros again. Thank you so much.
Thank you very much.